Let's talk about the future of our cities. Specifically, one of the biggest and loudest hurdles for that future, the noise from flying taxis. It turns out there's a surprisingly simple trick that could make them quiet enough to actually fly over our heads. Okay, let's get into it.
You've seen the concepts, right? These electric vertical takeoff and landing vehicles, or eVTOLs, just zipping across the skyline. I mean, it's an amazing dream. Clean, super fast, on-demand transport. But hold on a second. What would a city with hundreds or maybe even thousands of these things actually sound like?
And that, right there, is the big problem. On one hand, you've got this incredible dream of solving city traffic from the air. But the reality? Well, it could just be a constant, unbearable drone humming over our heads all day. And pretty much everyone agrees that noise is the single biggest thing holding this entire vision back.
So if we're going to fix the noise problem, we've got to understand where it's coming from in the first place. Let's dive into the science of how these rotors actually make all that racket.
Think about it. One little drone buzzing past is one thing, but these flying taxis need a whole bunch of rotors to get off the ground and stay stable. And it turns out when you pack all those rotors close together, they start messing with each other's airflow, creating a sound that is way, way louder than just adding up the noise from each one by itself.
And we're not just talking about some general whoosh sound here. The real issue is something called tonal noise. You know that very specific high-pitched whine that a drone makes? The one that kind of gets under your skin? Yeah, that's it. It has a specific frequency, and it's the part of the sound that humans find most annoying.
So here's where it gets interesting. By default, the blades on these vehicles are often spinning in perfect sync. They're all in the same position at the same time. This means the little tornadoes of air spinning off the tips of the blades, called tip vortices, end up slamming right into each other. That collision creates total chaos in the air, and all that turbulence is a huge source of that annoying whining sound.
Okay, so that's the problem. But what if there was a really elegant way to just stop that collision from ever happening? Researchers have been looking into a technique that is just brilliantly simple, but wow, is it effective.
The solution is called phase synchronization. All it means is that instead of letting the rotors spin in perfect time, you program them to have a slight delay. You just intentionally offset their timing from one another. It's not about changing their speed, just when each blade hits a certain point.
So in this study, the researchers tested a very specific offset, just a quarter of a turn, or a 90-degree difference. And the result is kind of amazing. By the time the air vortex from one blade gets to the middle, the other blade is already gone. They just miss each other completely. The vortices don't collide, and the airflow suddenly becomes much smoother, less turbulent, and a whole lot quieter.
But it gets even cooler than that. It's not just about making the air smoother. As the researchers put it, this timing offset actually creates interference in the sound waves themselves. I mean, think about it like noise-canceling headphones. The sound wave coming from one rotor is timed just right to cancel out the sound wave from the other. You're literally using sound to fight sound.
Now, you can imagine that proving this theory with real, full-scale prototypes would be incredibly complicated and expensive. So instead, researchers did something smarter. They built a perfect virtual wind tunnel inside a supercomputer.
So here's basically what they did. First, they built this flawless digital model of a two-rotor system. Then, using some seriously powerful simulation software, they modeled every little swirl and eddy of air flowing around the blades. From that data, they could then predict exactly how the sound would travel and what you'd hear far away. And then, they ran the whole simulation twice, once with the rotors in sync and once with that 90-degree offset.
All right, so this is the moment of truth. What happened when they compared the two simulations? This is the payoff, and honestly, the results are what make this whole thing so exciting.
What they found was a noise reduction of up to 5 decibels. Now, I know, 5 might not sound like a huge number, but the decibel scale is kind of tricky. A 3 decibel drop is actually cutting the sound energy in half. So 5 decibels, that is a really noticeable, significant decrease. It's kind of like the difference between a loud, busy office and a quiet library.
And check this out, this shows you exactly where it gets quieter. On the left, you've got the standard setup. It's projecting this big, intense cone of noise straight down. But look at the one on the right with the offset rotors. That downward cone is way, way smaller. It creates this much quieter zone right underneath the vehicle, which is, exactly where we'd be standing on the ground.
So, the really important thing here is that this trick specifically targets that annoying, whining tonal noise we talked about earlier. The sound waves are timed so perfectly that they just cancel each other out through what's called destructive interference. The most annoying part of the sound is almost completely erased right below the vehicle.
Of course, there's always a trade-off, right? You can't just make energy disappear. So while the noise drops by 5 decibels directly below, the simulation showed it actually gets a little louder, about 3.5 decibels out to the sides. But here's the kicker. The noise levels in those directions were already super low to begin with, so a small increase there is a fantastic trade for that huge quiet zone underneath.
Okay, so let's pull back and look at the big picture. This is more than just a cool science experiment. It's a potential breakthrough for a whole new industry. So what does this simple little timing trick really mean for us?
Let's put it all together. We know that noise is the make-or-break issue for flying taxis. This research proves that a huge part of that noise comes from the rotors basically fighting with each other's airflow. But by simply offsetting their timing, which is just a software change, we can use physics to our advantage, letting sound waves cancel each other out. It creates a cone of relative silence right where it matters most. Now, it's not a silver bullet, but tackling the most annoying part of the sound is a massive step towards making these flying vehicles a quiet reality we can all live with.
And that really leaves you wondering, doesn't it? We're always looking for these huge, complex solutions to our biggest problems. But sometimes, as this research shows, the most powerful answers are hidden in something as simple as